Hello everyone and welcome back to the NPTEL online certification course on aquatic geochemistry. We were discussing the water sampling techniques and the importance of filtration in our last lecture, and we will continue to discuss about the water sampling techniques in this lecture as well. Now, first things that we would discuss is the parameters that we are going to measure. What are the parameters that we measures? And first kind is physiochemical parameters. Now, whenever you are going to take a water sample, as I said that we always need to have an entire picture, and there are certain different categories of data that we need. So, the first kind is the physiochemical parameters, second is the dissolved concentration, and third important information comes from the particulate constituents and particulate concentration. What are the physical parameters, right? Now, physical parameters, for example, pH, okay. pH is the most one of the most important physiochemical parameter. Then there is temperature, okay. So, in always all the time you will see the data for temperature and pH will be measured for water samples, okay. Then another important parameter is dissolved oxygen, okay. So, dissolved oxygen again an extremely important parameter, not only for aquatic life, how much aquatic life it can sustain, not only for that reason, but also to understand metal variability, particularly those metals which are redox sensitive. So, dissolved oxygen is a very important parameter here. Then you can have electrical conductivity, okay, electrical conductivity or EC, okay. Then salinity, okay. Salinity is how salty that water is, how much NaCl or KCl is present in that water. So, salinity is a very important physiochemical parameter. It controls the ionic strength of water and therefore, a lot of ionic interactions. So, it is a very important physiochemical parameter. Some other physical parameters can be color, okay. It can be hardness, okay. What is the hardness of the water? What is the turbidity, okay. What is the turbidity of water? Then what is the total dissolved solids, okay. So, what is the total dissolved solids, that can be there, okay. And the total suspended solid, okay. Total suspended solid, that has to be measured. So, total suspended solids, okay. So, these are the few parameters, okay, that is required to be collected in situ. What is meant by in situ? That means when you are measuring the, when we are collecting the sample, you are going to take the measurements then and there itself. Only except those times that you do not have any other way will you take the sample back to the lab and then measure. So, what happens is when you are taking the sample back to the lab, your temperature can change, your DO can change, okay. So, these parameters can easily change, okay. What may not change is maybe the electrical conductivity or the pH or the salinity, that may remain constant for some times, right. But for other parameters like temperature, specifically temperature, dissolved oxygen, it is always, and also for alkalinity, okay. So, what is the alkalinity? It is important that you take the measurement in the field itself, okay. So, this is the physiochemical parameters, and it is important to understand and have knowledge about these parameters, because these parameters control the concentration of the dissolved constituents and their interactions with the particulate constituents, okay. Now, dissolved constituents, particulate constituents, for both we will need this, we would need this periodic table here. Now, in this periodic table I will talk to you about the categories in which we divide the chemical analysis. Okay. So, in every kind of water, the first thing that we are going to measure apart from the physiochemical parameters will be its major ions, okay, that is major ions. Now, major ions, the concentration in the dissolved stage is divided such that whatever is there that is more than 1 ppm is called major. Okay. So, that forms a major ion. Okay. So, whatever is there more than 1 ppm is one major ion. Another is trace concentration. So, this is trace concentration. So, whatever is below 1 ppm, okay, we call that either trace elements or trace metals. Okay. Now, major ions, they are of two kinds. Okay. One is cations, that is they are positively charged, and the other is anions, okay, they are negatively charged elements. So, here if I show you sodium, potassium, magnesium and calcium, these are our 4 elements which falls under the major cations. Okay. So, sodium, magnesium, potassium, calcium and from here silica. Okay. These 5 elements is commonly called as the major cations. Why? You may think that why is some major, some minor. Now, sodium, potassium, calcium, magnesium, they form the building blocks of life, right. So, apart from oxygen, hydrogen, nitrogen, they are the building blocks of life. So, you will have a high concentration of sodium in your body, potassium in your body, your bones are made of calcium, magnesium. So, in our physiology they are there. Okay. So, due to the interactions with physiology and also with rocks, right. Now, rocks forms the first hand contributor to any kind of river chemistry or lake chemistry or groundwater chemistry or ocean chemistry. The the earth's surface, okay, the rocks that is there on the earth's surface, they control the first hand chemistry, right. Now, these minerals that is found most commonly are enriched in sodium, magnesium, potassium and calcium, and of course, silica is the most abundant element in the rock. So, silica will also be extremely in high concentration and it will be a cation, like a major cation in most of the water samples that we collect. Okay. What are the anions? So, when there is some positively charged constituents in the water, to balance the charge balance, there also has to be a negatively charged particle. So, anions will be my fluorides, my chlorides, okay. These will be my nitrates, my sulfates. So, these are my anions. Okay. So, the most common ones are fluoride, chloride, nitrate, okay, nitrite and nitrate both are there, and sulfate, okay, and phosphate. Okay. So, these are there in the water, and whenever we are going to measure the anions, we are going to measure these, at least these 5 if not more. Okay. We can go for bromides, we can go for nitrites, ammonium and all that. So, but these will be our major anions. Okay. After cation analysis is done, after anion analysis is done, we understand how the water is behaving, that is how much contribution is coming from rainwater, how much contribution is coming from the weathered system, how much contribution is coming due to bicarbonate carbonate weathering, silicate weathering. So, such divisions can be made just by analysis of the cations and anions in the water, and this I am talking only about the dissolved water. Okay, what is there in the dissolved phase, not in the particulate phase. In the particulate phase, the major ones will be different. It will be silica, SiO2, there will be Al2O3, okay, there will be Fe2O3. So, these ones will be the major oxides that we are going to measure in the particulate phase. Now, what is there in the trace concentration? All the other elements will be there in the trace formation, and some kind even sometimes it can be in the ultra trace, okay, ultra trace, or it is called rare concentration. Okay. So, these concentrations they will be very low. It can sometimes be from few ppb to ppb to ppt, that is parts per billion to parts per trillion. So, you are moving from parts per million, okay, to parts per billion and parts per trillion level. And not every kind of water has similar concentration in particular elements, like same kind of elements. So, if you have river water, if you have ocean water, if you have lake water, the concentration of each element will be different in the different aquatic ecosystems. Okay. And this is due to the processes that they are subjected to, this is due to their inputs, due to a lot of parameters that controls finally their composition. And let me now say that what are the particular elements that we measure in the trace elements. So, we will measure lithium, we will measure beryllium, we will measure rubidium, strontium, caesium, barium, we will measure vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, then we will measure aluminum here, okay. We will measure arsenic here, we will measure lead, we will also measure uranium, we can so these are the commonly measured trace metals, then sometimes we can also measure cadmium. So, these are mostly the trace metals that we are going to measure in the dissolved state. Okay. Now, some of the measurements are also done in the form of nutrients. Okay. So, nutrients, what are nutrients? Nutrients are food, it is like food for the aquatic plants, for the aquatic animals. So, they will be the nitrates, okay. So, NO3. So, then we are going to measure whatever N is there in NO3, whatever N is there as NO2, whatever N is there in ammonia, okay. So, whatever the N is there in the different forms of nitrogen related compounds that is there in the water. So, N is there, then P is phosphorus, that is there in the form of orthophosphate. So, that is there. So, P of PO4, and then you will have silica. So, silica that is there in the dissolved state. So, Si of SiO2. So, this is the nutrients. Okay. So, these are the nutrients that we are going to measure in water. Again, there are some more measurements. So, in water that we are going to have to measure oxygen, we can also measure carbon, right. So, now, for carbon there are many different types of analysis. The most common analysis that we are going to do is the TOC, that is the total organic carbon that is there, and the dissolved organic carbon. So, the TOC consists of two things, that is particulate organic carbon and dissolved organic carbon. okay, how much organic carbon concentration is there in that particular water. So, that is my DOC, and whatever is there in the particulate fate, that is my POC. Okay. So, my TOC will be measured, DOC will be measured, and similarly we can also measure, you know, for nitrogen we can measure TON, that is my organic nitrogen, DON, that is dissolved organic nitrogen. Okay. So, for carbon, for nitrogen, these kind of measurements are very commonly done. For others, say for example, for particular elements we do particular other analysis. Say suppose for oxygen, DO is already measured, right, DO is already measured as the amount of oxygen that is dissolved in the liquid, but certain elements can be used as tracers, right. So, we will be using them as tracers. Now, tracers has to have the uniqueness. Okay. Uniqueness means for every process their values should be different. Otherwise, if the value is same or overlapping, how will you know whether it is process X and not process Y? Okay. So, for different processes, okay, the tracers has to be unique, and mostly we find that isotopes, okay, are great tracers. Okay. Isotopes work great in as tracers. What are isotopes? Okay. We will come to this particular, you know, lecture about what is isotope and how many, you know, what are the different, you know, there are broadly two categories, that is one that is radioactive and the other that is stable. Okay. So, there are two types of tracers, we will use radioactive isotopes and we will use stable isotopes, and mostly the common ones are oxygen isotopes, carbon isotopes, nitrogen isotopes, hydrogen isotopes. These are very you know traditional stable isotope systems. Strontium here is a very you know widely used radiogenic isotope system. So, the samarium neodymium system, this is another extremely used radiogenic isotope system, and now many more stable isotope systems are used to, you know, as particular tracers for particular elements. For example, you know that, you know, this is our it can be called as macronutrients, right. So, if your body is lacking calcium, if your body is lacking magnesium, sodium, potassium, the doctor will give you tablets like, okay, you take this calcium tablets, you have calcium deficiency, you have, you know, sodium has gone down, so he will be giving you some tablets. So, like that, these are our major nutrients, it is absolutely required in you know big concentrations by our body. And then there is something called micronutrients. Okay. Micronutrients, for example, you know, cobalt, nickel, copper, zinc, these are extremely important because they are part of these enzymes and they can, you know, be, you know, in the structure of the molecules that is there in hormones, and for our you know physiological processes, all these elements they are required, you know, in certain small concentrations. Okay. So, these particular, you know, elements, not only 4 elements, there are many other elements that I am not pointing out right now, but there is a category of micronutrients. So, by the nature of these elements, that means they are interacting with the physiological processes. That means when I am seeing them, when I am trying to understand their behavior in water, then there will be much more you know biotic interactions, right. That means their distribution, their variations which will be much more complex than say for element which is you know not of biotic nature, say for instance lead. Okay. Lead is a element which is not required by our body for any kind of physiological functioning, right. So, it is there, if it is consumed it will just stay there, or it can get excreted out, but generally lead tends to accumulate in the body. So, these kind of elements are actually toxic elements. So, that means they are not required by our body even in a very minute fraction also, minute small to small concentrations also our body does not need it, and sometimes it can show the diseases, right. Sometimes it can actually be very fatal also. So, deaths and also can happen. So, those elements are called toxic metals. Okay. For instance, lead and cadmium, these are carcinogenic, and for instance arsenic, here a lot of skin diseases are happening. Okay. So, many different types of metals, they can be of the toxic category. Mercury, another very toxic element. So, different types of analysis we have to do, and we have to find out what is their concentration. Now, the type of sampling that we are going to do and their sample preservation techniques depends on the research question that we are going to address. If my question, if my scientific understanding is whether how much water is coming from the different sources. Say for instance, I am taking a lake. Okay. In that lake, how much water is coming from groundwater, how much water is coming from rainfall. I want to constrain that. Then what I will use? I will use stable water isotopes, and using stable water isotopes, okay, I can do source apportionment. Source apportionment means that I want to calculate, I want to quantify the contribution from each different source end member. So, for example, for rivers, okay, it can be rainfall, okay, or it can be from snow melt water, or snow melt, I will write snow. It can be from groundwater, okay. It can be from ice melt water, okay. If it is coming out from glaciers, that can be there. So, the contribution of rainwater, the contribution of groundwater, the contribution of ice melt water. So, how much water is coming from these end members into this system. Okay. If I want to do that kind of study, I will use stable water isotope information. If my question is related to understanding the weathering, okay, weathering is one of the processes that consumes carbon and it removes carbon from the atmosphere. If I want to do those kind of studies, I will definitely first have to quantify what are the major cations, what are the major anions. I will to try to quantify what is the DIC, what is the alkalinity, and I may also have to use strontium isotopes to understand the carbonate weathering versus silicate weathering and things like that, and how much interactions is going on with the suspended sediments and the bed load sediments. Again, if I want to understand what is the water quality, okay, of that particular aquatic system, I would measure major cations, I will measure major anions, I will measure few target elements, okay, if not all is definitely the best thing that can happen, but at least these elements we need to measure, okay. For instance, iron, copper, cobalt, cadmium, mercury, lead, arsenic. Now, mind you, these are micronutrients. That means, if it is uptaken in very small concentrations. If their concentrations are beyond a certain value, then they also exert harmful and sometimes diseases can also be caused due to the excess uptake and presence of these elements in the water. Okay. So, therefore, these elements are there and certain elements are absolutely toxic. Okay. So, this group is absolutely toxic. So, pH, alkalinity, chemical oxygen demand, these kind of information, this data definitely is required for water quality inorganic kind of analysis. For organic analysis, what do I know? I need to know the biological oxygen demand, I need to know how much organic carbon is there, how much organic matter is there, how much nutrients is there, whether it is moving towards a eutrophication or not, what is the chlorophyll content, okay, whether there is algal bloom or not, okay, what is the microbial load, what is the viral load, how many plant species can I identify, if I can identify some of the fish species, whether the this kind of analysis of plants, birds, insects, fishes, they help us understand whether the system is healthy or if there is some kind of stress, because if there is any kind of stress, aquatic life will immediately start showing symptoms. Therefore, bioassessments are actually a very good indicator of water quality. So, bioassessments are often done to see that whether how the ecosystem is responding to different interventions and all. And apart from this, there can be a multitude of process oriented studies, okay, and you can variety, there can be no limit to the kind of processes you can do, and those kind of studies mostly be using multiple types of data sets, and the most important ones will be the usage of isotopes. So, not only the major cation, anion and trace elements will be moving towards tracer based analysis and specifically target tracers. So, if the process is more geologically dominated, then we will go for geogenic tracers, for example like lithium, rubidium, strontium. Now, these metals are extremely mobilized during the weathering activities. So, therefore, the natural weathering of rocks, they control the concentration of these particular elements like lithium, rubidium, strontium. But for certain other elements, for instance lead, okay, lead is not a element that is found in a significant proportion on the earth's surface. It was mined and it was used for a specific purpose, and therefore, due to this anthropogenic usage, due to this anthropogenic mobilization, lead now is much higher in concentration on the surface of the earth, that is the surface environment of the earth, as what it would have been if it was not used by humans. Okay. So, the particular uses of different metals makes them more mobilized across our environment, and if it is anthropogenically done, we call them as anthropogenically mobilized elements. And there can be, of course, other parameters are also required to understand these process oriented studies. For example, this biological and micronutrients like iron, copper, zinc, discharge and other parameters. Now, process oriented studies we will be discussing in when we are discussing the global geochemical cycles, particular for example, how much is interacting between the sediment and the water itself, okay, how much interaction is going there. So, we can use strontium isotopes there, and how much uptake and uptake is happening from the river to the plants and coming back to the system, what is those microcycling is happening. So, again those kind of processes, redox related processes, those are examples of processes. Okay. So, those kind of studies, for them we need multiple types of data and especially tracer based data. And when we collect these samples, every type of sample is collected differently, and that is because for different types of analysis the instruments are different. Okay. The same instruments is not used for all kinds of analysis, right. So, when we collect samples, we have to collect them in different bottles, and some of these samples will need preservation, some of the samples will not require preservation. For example, major cations are they, if you are drinking water in a plastic bottle, often you will see that after a certain point of time the bottle has some white precipitation inside of the bottle. What has happened? That maybe the water was hard water, so calcium, magnesium and all that has precipitated outside. So, if you are measuring calcium, then it is actually different than what the actual sample was, right. So, because the calcium got precipitated out, so you do not want that to happen for your sample, because then you will have erroneous data. You are not measuring the real calcium concentration then. So, to prevent such kind of precipitation to happen, we add a few drops of acid to the sample. Okay. Then the acidified sample, there is no precipitation, all the cations they are in their ionic form, they will not tend to precipitate out. So, for example, DIC, DIC, if I am taking a sample for dissolved inorganic carbon, for which I have to measure the alkalinity and all that, I have to use glass water bottles. Okay. So, glass water bottles, there should be no head space, but it means there should be no gap between the water and the cork. Okay. So, it is absolutely full to the there is no head space, and there has to be glued. Okay. It has to be glued such that there is no atmospheric exchange. Okay. For nutrients, okay, the sample may have to be poisoned or it may have to be stored frozen, so that there is no kind of microbial growth that will consume the nutrients. Okay. So, due to the changes that can happen during our sampling shipment. So, when the sample is collected from that location to when we bring it to the lab, during the shipping process, whatever losses will happen, we have to take care that there is minimal losses, and that there is the sample is intact. So, therefore, we use different types of water bottles. The bottles can vary. For instance, some of them here you will see are plastic, some of them are glasses. So, for cations, anions, nutrients, they require plastic bottles. For TOC, for alkalinity, for mercury, they need the glass bottles. Okay. So, different kinds of bottles are also used, different kinds of preservatives are also used. Okay. So, these kinds of carefulness we have to maintain when we are taking our sample. Okay. Otherwise, our data that we are going to produce after so much of hard work, they will show error. And sometimes if I am taking say for instance, I am giving an example here, there is a I am going to measure water isotopes. Okay. Now, for water isotopes, I have to fill the water up to the brim, that means that when I close the cap, there should be no head space. Now, what if I am not careful? What if I allow there to be a head space? Then there will be evaporation, and also I have to seal the bottle such that there is no exchange with the atmosphere. What will happen if I am not careful, if I am not filling it up to the full, if I am filling only half the bottle and there leaving space here, what will happen? There will be atmospheric exchange. When I collect 20 samples and bring to my lab and I analyze, I will see that all of them are showing me random values or maybe the same values. Okay, because they have exchanged with the atmosphere and now they are showing me the same values, or they are showing me random values. Then I know, okay, that some error was occurring during the sample collection or during the sample shipping. So, therefore, I am getting such kind of erroneous data. Now, with this I will end the lecture today, and I will discuss further kinds of things that we need to take care of when we are going for sampling. Okay. Thank you, and see you in the next lecture.